As the title says, this video lesson covers exponential growth from sections 6.2 and 6.3. You should definitely have the exploration sheet for sections 6.2 and 6.3 when you watch this video. Most of this video is, or pretty much all of this video, is about that exploration. You've probably already covered number one from the exploration sheet in the classroom with us, but let's just review it real quickly here. We need to rewrite each of these statements using the description. So y is directly proportional to x. We know that is written as y equals k times x, and then inversely proportional to x is y equals k divided by x. So how about y is directly proportional to the square root of x? All right, so y is equals, and then directly proportional we know means k times something, all right, and then the square root of x. So it's k times square root of x. And for the last one, this is for calculus students, we have that the rate of change of y with respect to x is inversely proportional to the square root of x. So rate of change of y with respect to x, that should be telling you as a calculus student something very specific. And even when we just use the word rate, we know that that is referring to d something over d something. Usually it's d something over dt. In this case, rate of change of y with respect to x is dy dx is inversely proportional, so k divided by, and then we've got the square root of x. So be looking out for that kind of wording as you work through this chapter. All right, so the situation that's presented to us in number 2 is that we're putting $1,000 into a savings account that's earning a whopping 5.127%. Yes, there was probably some magic fairy dust sprinkled on this bank. But anyway, after t years, the amount in the account is given by capital D of t equal to 1,000 times 1.05127, all raised to the t. And that's, of course, that's what you're earning every year, and t is the number of years. So let's complete the table below, and ultimately we want to figure out what goes in this r of t column. Now the first two columns shouldn't be too much of a problem since they gave us d of t, and as calculus students we should be able to figure out d prime of t. Feel free to open a list and spreadsheets page of your calculator. You will need to label each column, or give each column a title. So you go to the very top of the first column, you could call that years if you'd like. You can't just use T for a title of a column, it has to be more than one letter, all right? And then you would come down, skip over the second row. I'm not showing the second row in my table, but you'll skip over that and just come to the third row on the calculator and just type in 1, 5, 10, 20, and 50. And then over here, D of T, yeah, you could label that dollars if you'd like. And then in the second row, of course, there what you would put in would be, and this is kind of the formula row. All right, it would be 1,000 times the 1.05127, and then you want to raise that to your years column. Okay, and you can find that easily if you want to hit the vars button. But that's what you want to do, and then that'll give you all the y values for each of these years, or all the dollar values for each of those years. All right, and then of course to get the derivative, feel free to use your calculator if you like. Of course, we do know how to get derivatives of exponential functions, but if you want to use your calculator to get that, and once you have that formula, then of course you're still plugging in t as your independent variable. Okay. Certainly another way that you could approach this if you want to open up a new page in this problem would be to let this function here, let's see, you could let d of t be f1 of x, and then when you get the derivative, you could let, store d prime of t as, you could store d prime of t as f2 of x. Okay, so then when you come down to the column and you have to enter the formula, you can say equals. By the way, it should automatically give you equals, but if it doesn't, you would need equals. And you could just say equals f2 of x. Let's see if I can get that there, yes. f2 of, I'm sorry, not f2 of x, but f2 of years. Okay, and then it would give you those values. So take a little bit of time and see if you can get that, and then you fill in the values on your sheet. All right, check it out and see if you got the following. This is what the table should look like with those new values. Okay, keep in mind my table and your table on the sheet of paper is not showing a formula row that you have to plug in to get some of these things. All right, so just looking at these numbers here, we've got d of t and we've got d prime of t. Let's just answer this basic question here. Does the rate d prime of t stay constant as the number of dollars in the account increases? So as we see the dollars go up, is this rate, the d prime of t rate, is that staying constant? I think pretty quickly we can say not only no, but heck no, right? It certainly is getting bigger and bigger as the number of dollars increases, okay? Now it asks us, let's see, so I'll write a little no here for that question. Now it also asks us to interpret the meaning of d prime of 5 in terms of the problem situation. All right, now we have that d prime of 5 is equal to 64.2. All right, but now we know this is a rate here, okay? We see the units dollars per year, so let's write this as 64.20, and let's write it as a fraction over 1, and let's put the dollars up top, right? And we know the years go in the bottom. We were doing this like way back in chapter 2. We were interpreting rates. So this is just a little bit of practice doing that. So go ahead and write out a little sentence down here, on your sheet of paper that describes what this rate means, okay? Just notice I use plural there on the years, but that should just be singular. So scratch that out because it's 1 year. All right, check and see if you wrote something like this. Okay, so maybe there might be a couple of things in here that you didn't provide. One is I'm pointing out that this rate is only happening when t is 5 years, right? We can see that as we go up in the years, then our rate increases. So I did mention that. But the main gist of this is to point out that the number of dollars is going to increase by 64.2 for every increase of 1 year. So for each year that elapses or increase in 1 year. So notice I'm talking about whether the numerator increases versus the denominator increasing, and I also include the numbers here. You want to include both the numerator and the denominator numbers when you're describing it. Plus, I'm including the units. So I'm very specific here when I'm describing this rate, and that's what we were doing back in the fall semester. So this is good review of that. So now I want you to think about how could we fill in the last column here? How can we get this R of t? And the thing to do, and it says this in letter C, is focus on the units, all right? Here we have dollars per year for d prime of t, dollars per year. Over here with d of t we have dollars. And now we want dollars per year per dollar. That should kind of tell you what you need to do with these two columns to figure out this column right here. So give that a try. All right, see if you got the following. If I want dollars per year per dollar, that of course means I'm going to take dollars per year, so d prime of t, and simply divide it by d of t, my dollars. And a surprising thing happens when you do that, okay? If you did it correctly, you should actually end up with the exact same number every time here. All right, so what does this mean about the problem situation? Well, once again, we have a rate here that we could describe, okay? Our rate is 0.05. Let's put that over 1. And in the top, we have dollars per year. Per year. And in the bottom, we have dollars. So how would you describe this rate? All right, take what we did on the last in part B and see if you can describe this rate using some of the same language. Don't worry about the t values being right at 1, 5, or 10. It's happening the whole way. And the other thing I might suggest for this, try maybe describing the denominator first. That might be a little easier. Okay, so did you write something like this? Once again, you'll see I'm using both the numbers here, 1 and 0.05. I'm using the units that are given, and then I'm also determining or talking about whether these values are increasing or decreasing. And in this case, since they're both positive, we can say for every increase of $1, and maybe I should have been more specific in the amount of money, okay, probably should, let's add that in there, in the amount of money. I'll use the amount of money. Then the rate, okay, that's what we have, dollars per year up here. This rate at which D increases goes up. The rate actually increases by $0.05 per year. All right, so not only is the rate going up, but it's going up at a constant rate in a sense. All right, which is really why you've probably heard people say that if you have money, it's easy to make money. Okay, the more money you actually have in the bank, the higher your rate keeps going. All right, and that's why we see this increase in the rate. All right, so letter D kind of spells it out. If we let our function d of t just equal y, all right, so y is the amount of money you have after t years, or we could replace d of t with y here, then our analysis from part C indicates that the rate of change of y with respect to t, all right, that would of course be dy dt, we'll talk about that, is directly proportional to y. In other words, as the amount of money increases, the rate at which the money grows also increases. Write an equation depicting this statement, and then we should already know what the value for our constant k is in this case. All right, so this statement says that the rate of change, that dy dt, the rate of change with respect to t, okay, is directly proportional, so k times directly proportional to y. Now, if we think about how we got this column over here, this should make sense, all right? We took our derivative, which we're now calling dy dt, all right? So we took dy dt, we divided it by our dollars, which now we're calling y, and that gave us 0.05. So if we just multiply both sides of this equation right here by y, then that would basically give us the direct proportion, right? We would be left with dy dt is equal to 0.05 times y, and so of course that means that our k, our constant, is the 0.05 that we got up here. All right, well, we're going to move on to the back side of the sheet now, so flip that over, and what we will do is see how we can solve, this differential equation right here for y. So we're starting with this differential equation. We want to separate the variables and then integrate both sides to try to get the absolute value of y by itself. You'll see why we have absolute value of y here. All right, so let's see. Looks like I'll need to get the dt over the other side and then bring the y over to the left-hand side. So see if you don't agree, that would give us, 1 over y times dy equals 0.05 times dt, and I think it's wise just to leave the 0.05 on the right hand side. It can go either place, but it'll be easy to integrate if you leave it on the right hand side. All right, so now we're ready to integrate both sides. So we have the integral of y to the -1 dy equals the integral on the right side. I think what I will do is pull the 0.05 outside the integral since that's a constant, so I just end up with the integral of 1 dt. Okay? All right, so now on the left-hand side, let's integrate with respect to y. We've got that y to the -1. Yes, that's going to require that we use our natural log rule, so we'll have the natural log of the absolute value of y, that's where that absolute value comes from, equals, and over here we have 0.05, of course the integral of 1 with respect to t is just t, and then don't forget, we need to do plus c right at this point, very important. All right, and now let's solve for the absolute value of y, so we just have to get rid of our log over here. How do we get rid of a log? Exactly, we use its inverse, and the inverse of a log is, of course, the exponential function. So let's change this to an exponential. Our base on the log is e, so we're going to have basically that the absolute value of y is equal to e, this e raised to this power over here, right? So that would be e raised to the 0.05t plus c, and you see that plus c is up there in the exponent with the 0.05. Okay, so we have solved for the absolute value of y. Let's look at the next piece. We say the integrated equation from the previous part will contain e raised to a power containing two terms. That's what we have there. Write this power as a product of two different powers of e, one that contains the time variable and one that contains no variable. So in other words, remember now when you're adding exponents, that indicates we're multiplying two things. So we've got the absolute value of y on the left-hand side, and we could write this as e to the 0.05 times t, all right, times what? That we have that plus. What causes us to add exponents? Well, indeed, it means that we would have e to the c power, right? As long as our bases are the same, then what we do is we add the exponents. So we're just kind of going the opposite direction with that, the rule that you usually use here to combine two terms. Okay? Now, it says when you raise e to the constant c, you get another constant c that, okay, I mean, we could call this c sub 1 and c sub 2, but we just in the end we'll just call it c. Okay, so thus we can rewrite the equation as the absolute value of y equals, we've already got our e to the 0.05t, so we're just going to write in c in front, right? That's what used to be e to the c, okay? But e raised to a constant is just some constant, so that's how we do that. All right, and the last piece before we go to the other side of the sheet is explain why we can just drop the absolute value sign to get y equals c times e to the 0.05t. Well, we could maybe work it out with some algebra and so forth, but let me just point out that, you know, c came from e to the c. Now we know e raised to anything is a positive number. So this has to be a positive number. And over here we have e raised to something. So both of these numbers have to be positive. So our absolute value of y is going to have to end up being positive. Therefore, I think we can argue that we could just drop the absolute value and just call it y equals c times e to the 0.05t. Okay, no matter what you plug in for t, this side's going to have to be positive, so therefore our y is going to end up being positive anyway. Let's now go to the other side of the sheet. I've written up here where we left off. We have this equation, and they told us at the very beginning of the problem that the amount of money, our initial amount was $1,000 at time t equals 0. So let's use that information to figure out what c is, right? And perhaps you already could kind of guess what c is going to be, but we'll plug it in. So our output amount of money we have is 1,000, so that's our y. It's going to equal c times e to the 0.05 times 0 power. And of course that gives us 1,000 equals c times e to the 0, and e to the 0 is just 1, so we end up with c equals 1,000. So we now have that y is equal to 1,000 times e to the 0.05 t power. Now we see in letter J, we're suggesting that this new formula that we just got here is actually identical to our original equation, 1,000 times 1.05127 to the t. Let's show that it is. Okay, so most things seem to be the same. We've got y equals, we've got 1,000, okay? We need that t appear to be outside some parentheses, so I think we can rewrite this as e to the 0.05, and then outside the parentheses raised to the t power. And we know that our exponent, let's see, if we have a power raised to an exponent, we would just multiply the two exponents. So we're just going the opposite way with that. And now if you pull your calculator out and plug in e to the 0.05, you will get our number that we have there. So y will equal 1,000 times 1.05127 raised to the t power. Okay, so coming over to letter K now, it says, what quantity that you learned last year in pre-calculus does our K equal to 0.05 represent in terms of the CD savings account? So hopefully you remember that, back when you were doing exponential functions and you got into compounding with money, that K, if you have your growth factor equaling e to the K, that K is what we call the continuous rate. Okay, continuous rate. I think I spelled that correctly. All right. So if the bank was to tell you that your money was going to grow at 5% compounded continuously, okay, that would mean that you would just plug that number, 0.005. You'd raise e to that number, okay? And we're showing that gives us 1.05127. So what that means is ultimately, even though the bank said they were only going to pay you 5%, your actual yield, what you end up with at the end of the year, is 5.127%, which is, of course, the percent that we started with in our problem. We just weren't looking at it using this continuous rate, but that is what that K number is the continuous rate. And by the way, this number right here, the 5.127, that's what we call our effective rate. Okay, so even though the bank told us 5%, effectively we ended up earning more than that, and that's the way compounding works. All right, so what does all this work mean? Well, what it means now is that we've established that if we have a differential equation where the rate, okay, the rate is directly proportional to the output value. Okay, notice the y is the output value, or it's the variable, the output variable. It's the variable that's up here in the numerator of our rate. If we have this situation, then what we've figured out now is that we don't need to go through all that solving of the differential equation again that we did all the way, on this side of the sheet. All right, all we have to do is go straight and say, hey, look, we know that if we solve this for y, we're going to get y equals some constant c times e, and in this case, I don't have a k there, I have an r there, so I'm going to call it rt. All right, which we know is the exponential situation. Okay, in fact, you've probably used, instead of using c there, you probably use p there for principal, and what we have is pert. Okay, well, this differential equation right here, all right, when you have your rate directly proportional to your output variable, that will always yield this the exponential function. So you need to write this result up in your binder on the next slide. All right, so they spell it out on page 414 with exponential growth in decay that if y is a differentiable function of t such that y is positive and dy dt is equal to k times y, so the rate is directly proportional to the dependent variable, all right, for some constant k, then you know that y equals some other constant c times e to the kt. Or in other words, in shorthand, if you want to write it this way, that dy dt equal to k times y implies that you must have y equal to c times e to the kt. C is what we call the initial value of y, right? That's the starting amount, which you should recall from pre-calc and maybe Algebra 2. course, you're going to get C when t equals 0. That's why it's the initial amount. And then k is your proportionality constant. That would be in your differential equation. K is the proportionality constant. And in your solution, it's the continuous rate. Those are the same number, all right? So you can just go with that. All right, one more thing I'll add. I was running out of space, so I just moved my slide up a little bit. But we do know that growth is going to occur when k is positive, right? Think about it. If k is bigger than 0, well, if k equals 0, then we know e to the k would just equal 1. So if a is bigger than 0, then that means e to the k is bigger than 1, and we know that when we multiply by a factor that's bigger than 1, we're going to grow that initial amount. And of course, decay, therefore, is going to occur when k is negative, and that would mean that e to the k is going to be a number less than 1, right? Think about it like e to the, we'd be talking about like e to the negative 2, right? That would equal 1 over e squared, and that's going to end up being a number smaller than 1. So keep that in mind as you're working through the homework assignment. A lot of the problems on this assignment actually don't involve calculus. It's going to take some review and remembering how to do some of your pre-calc. We will discuss a number of those problems in class. So this does it for this video lesson. If you would like to try to work ahead, you might be able to get through some of the problems from the last 2 assignments on the assignment sheet. They kind of go together.